And here we are with another problem solving series. So today's problem is about an function and recursion problem which says us that consider a function f(n)x defined for positive integers n and real numbers x by f(n)x equal to sine of, like you can have n sine applications and then an x, right? For example, you take f of 2x as sine of sine x, f of 3x as sine of sine x, and so on. So basically what is our implication is that f(n)x is equal to sine of f of nx, n minus 1x, sorry, f(n)x equal to sine of f of n minus 1x. That is our basic implication. Now x is in between 0 to pi by 2, right? An open interval 0 to pi by 2. And the sequence is to be computed like f1, f2, f3, f100. Now it is found that for each fixed n, x, fixed x, and for sufficiently large n, the series approximates to a finite value, right? Like if you consider f1x, f2x, f3x, and up to fnx such that n tends to infinity, it approximates to root over of 3 by n. So it's an interesting result, right? Like whatever value you take for x and you are given a sine function, you apply sine many times, like infinitely many times, and it would approximate to a constant value, which you can say it to be approximated to root over of 3 by n, right? So do give it a try and please look into the solution after this. Let's move on to the solution part of the problem. So basically for the solutions, what we will do is, now before moving on to the solution, let me discuss some basic things, right, with you all. That is, suppose that the limit of bn when n tends to infinity, right, is equals to some value L, right? So let's suppose that the limit exists. So basically what it represents is that the limit exists. Then what I can say is that limit of n tending to infinity summation of bk k equals to 1 to n divided by n tends to limit of n tending to infinity bn, and now this tends to L. So basically this is known as the Stolz-Cesaro lemma. Stolz-Cesaro lemma. Right? You can search it on Wikipedia and you will get a nice web page dedicated to proofs and everything, right? So that is the thing that you can do. I won't be discussing about the theoretical aspects of this lemma. So that is it. Now basically what we need is this theorem to be applied here, right? So what we do is we basically define a bn, a sequence bn, such that bn, right? How do you define a sequence? You define a sequence as follows: bn greater than, for n greater than or equal to 1, and bn is defined as 1 by fn plus 1 squared minus 1 by fn squared, right? Basically this is how I define bn. Now then, what can you say about bn tending to infinity? For n tends to infinity, what about bn? So this also limit n tends to infinity for 1 by fn plus 1 squared minus 1 by fn squared, right? This is what I mean. Now you know that basically f of k plus 1 is equals to sine of f of k, right? Okay, so now wait. Basically what do I mean by f of k? So f of k is basically, this is fk plus 1 of x, that is what I mean, or that is sine of sine, and this goes on till k plus 1 terms, right? This series goes on till k plus 1 terms, and then an x, right? This is what I mean by f of k plus 1x, and then you can simply argue for f of kx, right? That is what I mean by this notation. So can you calculate this limit out for me? So what does this limit say is that limit of n tending to infinity 1 by, now wait, again another thing, that is, as x is fixed, right? You got that x is fixed. So therefore what you can say is that f of n x is fixed, right? This is also fixed, right? Now what you do is you take the value to be an, let us say that the value is n, then f of n plus 1 of x is basically sine of n, right? That's what I can say from this one, right? This is what I can say. So now then this becomes as sine squared an minus 1 by an squared, right? And then you can try this out. So this comes out to be an squared minus sine squared an divided by an squared into sine squared of an. And now this actually tends to 1 by 3. So let me write it down properly. Wait a minute. This tends to 1 by 3, right? Now that's an important and very interesting result, right? You got to see how we deduced that the limit of bn tends to 1 by 3, right? Now a further better result would come up is that we know that limit of bn as n tends to infinite. Okay, wait. Before that, how did we approach this to this? We can use L'Hopital. Okay, we can use L'Hopital, and that would give you the result very easily. So try it out on yourself. So then this is basically summation of bk, k equals to 1 to n divided by n, right? This is what I can say from here. Now that is equal to this limit of n tending to infinity 1 by n times summation of k equal to 1 to n bk, right? That is equal to limit of n tends to infinity 1 by n times, how can I represent this one, k equal to 1 to n? This is basically a k plus 1 squared minus 1 by a k squared, right? That is what I mean. Okay, so that is now limit n tending to infinity 1 by n into 1 by an plus 1 squared minus 1 by a1 squared. This is basically a telescopic series, right? How did we approach it? A telescopic sum. This is basically a telescopic summation, right? So that's how we approach it, and then this comes out to be limit of n tending to infinity 1 by n times 1 by, now how do you show this, that this is an plus 1 squared, right? And this is 1 by a1 squared. I just wrote it again. Now this can we write it as limit of n tending to infinity 1 by n into an plus 1 squared minus 1 by n into a1 squared. Now observe this thing. This is a fixed value, right? Does not, by fixed what do I mean is that it does not depend on n, right? If I vary n, it does not change, right? So what happens to this term is basically tends to 0. It basically tends to 0, and therefore we are left with only evaluating this term, that is 1 by n into an plus 1 squared, right? And I know that limit of n tending to infinity bn equals to 1 by 3. And now that is equals to 1 by n a n plus 1 whole squared, and the limit n tends to infinity, right? That is it. And therefore you get that a n plus 1 squared, you take the limit on this side, right, n tending to infinity. This is basically how much? How much is it? Calculate the values, and you would get it as 3 by n. Sorry. Was it 3 by n? Yeah, 3 by n. Yeah, 3 by n. Yes, it is 3 by n, and therefore you get it as limit of. Now this is limit n tending to infinity. Again, be very cautious about the limits. So what happens is that you can understand that a n plus 1 tends to. And now wait a minute, before this step, wait a minute. What I do is, now basically observe that as n tends to infinity, a n plus 1 squared is basically equal to the limit of n tends to infinity a n squared, right? So I can replace this value as limit of n tends to infinity 1 by n into a n squared. Now here is actually here's the trick. Here's the fallacy of the question, right? So what's the fallacy of the question is that it asks you to approximate, not exact value of the limit, right? It asks you to approximate the value of the limit. So that's the fallacy of the question actually. So then what you can say is that from here is that a n squared basically tends to 3 by n, and then you say that a n tends to root over of 3 by n, right? That's how you approach it. Now this is an important and very interesting result actually overall, and there's another method by which you can show this. That is, this is method number 2, and I call this as a vague method. Okay, this gives the answer, but it is not very much satisfying to do this, right? You take a n plus 1 and you can write it as sine of a n. Then what you do is you make this approximation as a n minus a n cubed by 6, right? And then what you do is you take these values to this side, and then you say that this is approximated to a n minus of a n cubed by 6. Then what you do is you basically take this as dA by dn. Like, okay, so wait. How do you approach this? Wait. So observe that the n values that you take, the value of, wait a minute, sorry. Let me change the color. Okay. So the value of n that you take, the delta difference, delta n is basically here 1. Right, so the delta n is basically 1. Now when I change this to dn, the difference will be also reduced. Dn, when it tends to 0, the difference will be reduced, right? And hence the values. So when I change it to dn, it basically becomes d of a by d of n, and that is basically minus of a cubed by 6, right? Because when the difference is very small, the value of a becomes constant, and therefore you can say that. But there's a fallacy, right? There's a fallacy of this method. The method is wrong at this step, right? There's a fallacy, big fallacy actually, big one, because the sequence is defined on integers. The sequence is as follows, that is a1, a2 and so on up to n. There is no a 1.2, right? There is no question about it. But we are still making some guesses and adding some new terms out of nowhere, and then you can always approximate. Actually this is basically a question on approximation, so that's where this question becomes a bit trivial, right? Or you can approximate. Actually this is approximations that we take into considerations. So now what you do is you take this to be dA by a cubed equals to minus 6, sorry, not 6, it's dn, right? Yeah, so dn by 6, and then you can pretty easily approximate that an tends to root over of 3 by n, again for this one also. So this also gives you the answer to the problem, but the thing is, this is not very satisfactory. The solution provided in this format is not so overwhelming or like enlightening, okay, and I prefer not to give this kind of solutions. So thank you everyone, and that's it for today. So see you guys in the next video. Thank you.